Welcome back. In this video, we're going to describe what is called Hess's law. We can use Hess's law to describe reaction enthalpies for reactions that require multiple different steps. To understand Hess's law, we need to review state functions. We learned about state functions initially at the beginning of the semester. A state function is a process or a function that does not depend upon the path or method used to get to a given state. It only depends upon the current state of the system. An example that we gave is elevation. Your elevation does not depend on whether you hiked straight up the tall face of the mountain or you took the long and winding trail. Your elevation depends only upon your actual location. However, the distance traveled does depend upon the path that you take. Enthalpy is a state function. In other words, it doesn't matter what path you take to get to a desired outcome, so long as you get there. From a given set of initial conditions to a given set of final conditions, the change in enthalpy will be the same regardless of if you did one chemical reaction or 100 chemical reactions. And so we can use this notion of enthalpy being a state function in order to determine the enthalpy of reaction in scenarios that might be a little bit complicated to actually measure in the lab. Hess's law describes this. It states that the change in enthalpy for an overall process is equal to the sum of the individual enthalpies of each step. Again, enthalpy is a function of the state. So it doesn't matter what steps you take so long as you get to a given endpoint. And we can use Hess's law to determine enthalpies of reaction for chemical reactions that are too difficult to measure experimentally in the laboratory. So let's say that we have one chemical reaction where we have A and it converts into B, and it has some change in enthalpy associated with that. Then we have B, which converts into C. And again, some amount of enthalpy is associated with that chemical reaction as well. What we can do applying Hess's law is say we can combine these two reactions together and sum together their enthalpies. And it's as if we converted A directly into C. And the change in energy will be equal to the sum of those two individual steps. So if you think back to when you learned about systems of equations and combining algebraic equations, this is the same idea. So if we look at this in a pictorial sense, let's say A is highest energy and C is lowest energy. Going from A to B is going to give off some amount of energy, and then from B to C gives off some other amount of energy. We could have just gone directly from A to C, and the amount of energy given off would be exactly equal to the amount of energy for the sum of the first two steps. So again, thermochemical equations can be treated as algebraic equations. We can add them together, or we can subtract them, or we can multiply them. And that's because, again, enthalpy is a state function, and enthalpy is a function of the amount of each substance. They can be added to or subtracted from each other. We can, any equivalent terms that are present on both sides of the equation can be canceled out in the same way as an algebraic equation. And we use these, what are called thermodynamic cycles, in order to determine the enthalpy of an overall reaction. So the thermodynamic cycle would be reactions number 1 plus reaction number 2 to yield reaction number 3. And reaction number 3 would be our enthalpy of reaction, the enthalpy that we actually care about. Let's go through an example. Say that we have 3 different chemical reactions. If we're given reactions A and B, we want to find the enthalpy of reaction for C. This is what we're given. This is what we want. And we need to apply Hess's law in order to get there. So this is going to involve some manipulation of the chemical reactions that you're given. Remember, we talked about how enthalpy is related to, it's an extensive property. So we can multiply by a given factor, or we can reverse the reaction in order to make it look how we want. So this is applying Hess's law that the sum of the enthalpies is going to be equal to the individual enthalpies of reaction times whatever factor we might multiply by. And again, there are two tools to use. We can reverse the equations, and that will reverse their sign, or we can multiply or divide by a specific factor, and that will multiply the energy by that same factor. So what we want to do is we want to obtain this given chemical reaction. So what you should do is you should identify a substance in the desired equation that shows up in only one of the chemical reactions that you're given. Notice that oxygen shows up in two different chemical reactions, but not in our final product. So trying to balance these reactions with respect to oxygen will be difficult. As long as you can identify a given element in each reaction that only shows up one place, then it doesn't matter which one you start with. So let's say that we start with looking at A and say that we are going to evaluate in terms of the aluminum. Notice that our final reaction has 2 aluminum in the reactant side, but reaction A has 4 aluminum. So what we need to do is multiply the whole thing by 1/2. So 1/2 of A. Looking at reaction B, you see that we have iron that's involved. Notice though that the iron metal is in the reactant side for reaction B, but the product side for reaction C. So what we need to do is we need to reverse the equation. In order to reverse the equation, we multiply it by a factor of -1. We need to do more than that though, because if we reverse the equation, we now have iron on the correct side, but we have the incorrect amount. We need also to divide by a factor of 2, or multiply by 1/2. So that will look like multiplying by 1/2 of B. Therefore, the energy involved is going to be equal to 1/2 of the enthalpy for A minus 1/2 of the enthalpy for B. So let's rewrite these equations. This is reaction A multiplied by 1/2. This is reaction B multiplied by -1/2. If we add these together, we get 2 aluminum plus 3/2 oxygen plus 1 iron oxide yields 1 aluminum oxide plus 2 iron plus 3/2 oxygen. And in the same way, when we've looked at molecular and net ionic and full ionic equations, same way we canceled out the spectators, we can eliminate anything that is extraneous, that shows up on both sides of the equation. You can then rewrite the equation and verify that it matches the equation you're looking for. So we want, in the reaction C2 aluminum, we have 2 aluminum, 1 iron oxide, 1 iron oxide, 1 aluminum oxide, 1 aluminum oxide, and 2 iron, 2 iron. So we know that we did it properly. Now, to find the energy involved, we take and multiply our enthalpy of reaction A by 1/2 minus the enthalpy for reaction B times 1/2. And that's going to get us -852 kilojoules. Here's one for you to practice on. I'd like for you to pause the video and try this one on your own. Welcome back. So we're given reactions A and B, and we want to find the enthalpy of reaction for reaction C. This is going to involve using Hess's law and rearranging reactions A or B in order to get the desired reaction. So we can apply these ideas that the sum of the reactions is going to get us reaction C, and the sum of the enthalpies will get us the enthalpy for reaction C. So what do we have? Well, for with reaction A, notice that it has sulfur dioxide in the reactant, and we have sulfur dioxide in our product. So we're going to need to multiply this reaction by -1 in order to get our sulfur dioxide on the proper side. However, notice as well that we have 2 sulfur dioxides in reaction A, but only 1 in the desired reaction. So we must also divide it in half. For reaction B, we can see that there's a common element of sulfur in both B and our desired reaction of C, but we have too much. So we need to multiply this by a factor of 1/2. So reaction C is going to be found by taking -1/2 of A plus 1/2 of B. Therefore, the energy change is -1/2 of the enthalpy of A plus 1/2 of the enthalpy of B. We can rewrite the equations after these modifications, sum them together to get our final equation, and cancel out any terms that are the same. Notice we get rid of the sulfur trioxide on both sides, and we get rid of 1/2 of the oxygen molecules on both sides, leaving 1 oxygen left over in our product, or our reactant, excuse me. That gives us then sulfur plus oxygen yields sulfur dioxide, which matches our equation. So we're confident now that we did it right, and then we can take and find the enthalpy. Okay, that's it for this video. Thanks for watching. Have a wonderful day.